So why go to all of this trouble, right? I was saying, sharp electrode recordings are a bit fiddly and people still did them for 20 years. People are still doing them, to be fair, but they should probably stop. Um, what's all the fuss about, right? So electrical signals are great because they're spatially resolved. Certainly, obviously to the point of not just a single cell, but compartments inside a single cell. What's the dendrite doing? What is the soma doing? The temporal speed, how the accuracy to which you can know when something is happening, there is nothing so far that can beat electrophysiology. So these two things combined, you can already see the advantage. Then, I would happily argue that for a second to second, moment to moment, maybe even minute to minute kind of the minute to minute behavior of the brain is best modeled purely electrically. There are biochemical signals going on. Obviously synaptic release is a biochemical, but you could ignore most of that chemistry with just the idea that action potential gets neurons to release neurotransmitter and forget about the biochemistry. Obviously, as things go on, learning and memory, gene regulation, these things take longer and they are obviously completely important. And so if you want to model how the brain works over the course of a year, you can't just rely on its electrical activity. But, why am I thinking what I'm thinking right now? That's an electrical thing. And so we need to have a quick reminder on bioelectricity because I know that was all of your favorite bits of CHP 311. We're just going to go through it really quickly, just so we know what we're talking about, right? So the membrane is a capacitor. It stores charge. You've got negative charges on the inside, positive charges on the outside. This basically means you've got also a battery because you have this separation of charge on one side, but you also have ionic gradients. So that means that charged particles want to flow. Then we have conductance, right, which is how easily these ions are allowed to flow. They obviously are always going to go towards their equilibrium potential, which is, the basically the direction tells you the direction of which the ions want to move, and the conductance tells you how easily they're going to move. So current is the flow of charge, resistance is how hard it is for current to flow, and resistance is just the reciprocal of conductance, and voltage is how much the charge wants to move. Sort of finally, charge cannot be created or destroyed, at least in a biological context, which means that current into an area is equal to current out of an area, which means for every positive charge that goes into a neuron, a positive charge must come out of a neuron.